So, length and location of the single stub in a transmission line in order to impedance matching. So, stub can do the impedance matching, means that the impedance of the source is equivalent to the impedance of the load, so that the maximum power will be transferred to the load. No reflections obtained from the load to source. So for that we are adding one single stub from here to here. This is short circuited stub. So now we are calculating the length of the stub and location of the stub. So this is the location. LS is the location of the stub and LT is the length of the stub. Now we are calculating those two lengths so that the maximum power will be transferred to the load from source. So we already know that the impedance of the transmission line is given by Z input is equal to Z naught into ZL plus J Z naught tan beta L by Z naught plus J ZL tan beta L. Now we are converting this into the admittance. Why? Because this short circuit stub and this load impedance both are in parallel. In parallel, the impedances simply we can sum instead of impedance in parallel admittances are simply we can add. For that we are replacing completely this Zn into the admittance. So for that we are replacing wherever the Zn is there 1 by Zn, and wherever the Z0 is there 1 by Z0, and wherever the ZL is there 1 by ZL. By doing both the sides, expression meaning cannot change. That's why. So here Z0 is there 1 by Z0, here Z0 is there 1 by Z0, and ZL is there 1 by ZL plus J. Z0 plus low 1 by Z0 tan beta L divided by 1 by Z0 plus J 1 by ZL tan beta L. Now, so 1 by Z in equal to Y in. Y means admittance. Now Y in equal to Y naught YL plus J Y naught tan beta L divided by Y naught plus J YL tan beta L. Now we are calculating the normalized admittance. It is obtained by dividing the input admittance with Y naught. Now by dividing with the Y naught, you can get the Y in equal to Y n in equal to YL plus JY naught tan beta L divided by Y naught plus JYL tan beta L. Now to get the complex number of or complex admittance, now we are rationalizing the normalized admittance. So here in this step we are doing the rationalization, that is divide and multiply this admittance with a Y naught minus JYL tan beta L divided by Y naught minus JYL tan beta L, and multiplying the numerator terms and the denominator terms. So in the denominator a plus jb into a minus jb, that is equal to a square plus b square, and multiplying the real and imaginary terms of the numerator result in the equation like this. Now this is the complex number, it having the real term and imaginary term. So now one point we have to remember. So at L equal to Ls, means location of the stub. And at that particular point, the admittance should be 1 plus JB, 1 plus JB. So 1 means real term, 1 means a real term. So that real term should be equal to 1. So now in the normalized impedance, when we are equalating the real term is equal to 1, L becomes Ls. Why? Because at that particular location, real term becomes 1. That particular location, the length should be equal to Ls. Now, at L equal to Ls, the admittance at that location becomes 1. So, by equating the real term equal to 1 and multiplying this denominator with 1 and equating both of the terms, finally you are getting tan beta, tan square beta Ls is equal to y naught by yl, and tan beta L is equal to square root of y naught by yl, and beta Ls is equal to tan inverse square root of y naught by yl, and Ls equal to 1 by beta into tan inverse square root of y naught by yl. This is the location of the stub in a transmission line in order to get the impedance matching. Okay, location is over. This formula you should remember. Now, how much length of the stub should place in the transmission line in order to get the maximum transfer? So now here our task is to find the length of a stub. Now at L equal to Ls, then the imaginary term what will becomes, the imaginary term is equal to y naught square tan beta Ls minus yl square tan beta Ls by y naught square plus yl square tan square beta Ls. Here in this case, Ls equal to what? Square root of 1 by beta into square root of y naught by yl, and beta beta gets cancelled. Now y naught square into square root of y naught by yl minus, and yl square into square root of y naught by yl divided by y naught square plus yl square into y naught by yl. Now simplifying this, finally you are getting Bs. What Bs indicates? It is the imaginary term. Impedance of a short circuited stub. Normally, so the stub internally having one impedance that is given by J Z naught and beta L. Now converting that into the admittance ys equal to 1 by J beta naught and beta L. Now in this case, the admittance of the stub should be minus J beta S, minus J beta S. That should be minus J beta S. Why? Because when we are adding admittances of the stub and the admittance at that particular location, so if the stub of the admittance is minus Bs and the admittance of the transmission line at that particular location is 1 plus Bs, by adding those two, 1 plus Bs minus JBs gets cancelled, finally you are getting the 1. So for that purpose, so admittance of the stub at that particular location should be minus JBs. So 1 by J Z naught tan beta Ls is equal to J into minus, instead of minus we are subtracting YL square minus Y naught square divided by YL square into semi-incremental. Now in this case, by solving this equation, now in this case L becomes LT by doing the equation, solving the equation, finally you are getting LT equal to 1 by beta tan inverse square root of y naught by L by y naught minus yl. So beta is equal to 2 pi by lambda. That substituting in place of the beta, you are getting LT equal to lambda by 2 pi tan inverse square root of y naught by L by y naught minus yl. So this is the finally length of the stub. So previously we have derived the location of the stub. Thank you.